Well, good afternoon, everybody. Thanks for joining. I hope everyone is staying safe and that you are all in good health. This is Priya Case. I'm the University Director of Sustainability and have been running the DG Hub now for quite a few years. And I just wanted to take a moment to thank the Sustainable CUNY DG Hub team and all of our partners across New York City and New York State, along with the subject matter experts that gave their time to support uncovering and preparing the information that we're presenting today. I really believe that this work has never been more important. I suspect I don't need to convince anyone on this call, so we'll continue to advance our work together and ensure that we're ready to move quickly to increase storage deployments when this pandemic ends. I want to encourage you all to reach out to us if you have any questions or thoughts about how we can be most helpful during this difficult time. So I want to hand it back to Daniela Leifer, who's going to provide some background on our work, and thank also Daniela, who's been instrumental, an instrumental member of the team and has really been helping to keep this effort moving forward. So Daniela, I'll hand it to you.
Okay, thanks very much. So my name is Daniela Leifer, and I am the project manager of Smart DG Hub with Sustainable CUNY, as well as one of the DG ombudsmen. The agenda for today's webinar is pretty straightforward. After brief introductions from myself and my other colleagues who will be presenting today, we'll take a brief look at the overarching goals and progress to date of the sort of the broader arc of our 9540a related work. The topic we're covering today represents one key component of that. Then we'll review the current landscape of standards relating to energy storage and how they differ and relate to specific product certification standards, as well as the UL9540a test methodology itself. Finally, the heart of today's presentation will be a walkthrough of our recently published guidance document, the New York City UL9540a Data Utilization Flowchart. As a project manager of the Smart DG Hub, I want to make a brief plug for how we approach our work of identifying solutions to barriers in the market, which is really all based around the engagement of a wide range of participants from industry, local government, utilities, subject matter experts, and really any other interested stakeholder group. We rely on your input to help us keep a finger on the pulse of what's happening in the marketplace. So we really want to hear from you and always encourage you to reach out to us for help and questions. And at the very end of this presentation, I will show our contact information on the screen. As just a bit of background on today's topic, as I mentioned, the New York City 9540a Data Utilization Guide is one outcome from a longer history of work that we've been doing, stretching back to early 2017, when we first launched our energy storage permitting work. We had about a year of weekly meetings with FDNY, DOB, and other stakeholders, which resulted in the publication of the first guidance document for permitting of outdoor lithium-ion battery systems in May 2018. This established the first set of permitting guidance for New York City, and one key sort of result of that was the identification of the requirement for large-scale fire testing. After that initial phase of work, we then began another roughly 9-month effort to really zero in on the many details surrounding this large-scale testing and how the data produced from the testing, would be applied to energy storage projects. It was a one question, but a really big set of answers going into that. So upon completion of the primary deliverable, which was a set of recommendations based on the best available thinking on this topic, we held a stakeholder meeting last November to introduce this to the broader stakeholder audience. Since then, we published this set of recommendations as a guide, as a separate document. That was just released about a month ago in March, and it is available on our website for access and downloading. And that essentially brings us to today's webinar, where we want to provide an opportunity for participants to get a guided sort of tour, if you will. And then finally, just before turning it over to Mike, who will get started on the standards landscape, I wanted to also make a brief plug for our updated energy storage permitting guide. This wasn't listed on the timeline on the previous slide, just because there wasn't enough room, but we updated this document as of this past February, and it now incorporates new permitting and siting requirements that were adopted by both FDNY and DOB during the past year in 2019. So this document looks similar to the first one in 2018, but it has been, pretty substantially revised. It is, of course, available on our website as well. Can be accessed there. Thanks very much, and Mike, you can take it away. Hey, Mike, just checking in with you. You might have some.
Can you hear me?
Yeah, there we go.
All
Muting
right,
issues resolved.
I know everybody loves hearing my voice. So I'm Mike Bose. I'm an Associate Engineer and DG Ombudsman here at Sustainable CUNY. Thank you guys so much for joining today, and hope you're all doing well. I'll just be giving you guys a very brief overview of the current standards landscape, as well as just a brief overview of a couple of the flowcharts here. So here, over the past few years, we've seen a shift towards battery safety, and that's in the form of NFPA 855, which is a standard for the installation of stationary energy storage systems, as well as the International Fire Code, IFC. UL has also developed a number of standards around energy storage components at different levels, such as 1642 at the cell level, 1973, 1741 for inverters, and 9540 for the system as a whole. Lastly, UL developed a test methodology for large-scale fire testing of energy storage systems, and that's UL9540a, which I'm sure you're all here to learn more about today. Requirements around energy storage systems are also given in New York State Code, issued by the Department of State. There was an emergency supplement added following the incident in Arizona. If you're not aware, there was a fire in Arizona in a 2 megawatt-hour storage facility in April of last year. And actually, during the time we've gotten this working group together to be going over 9540a, and we're covering the topic of deflagration and explosion hazard that actually happened. So we saw really how all these things are directly related, and how 9540a can be used. Also, New York City is unique from other parts of the country, given its urban environment and dense population. Therefore, more stringent requirements are necessary, and while these may seem like roadblocks for industry looking to develop in the city, they're really necessary, and we see that from past incidents. I also suspect that other municipalities will be looking at the work being done in the city and following that path. You can go to the next slide. So in the FDNY Rule, which was just published last October, 9540a is called out and is required for all sizes of lithium-ion battery systems in the city. They have a series of tables which lay out different requirements for different sizes and technologies of batteries. You can see that on the right, and again, noticing that it is required for all sizes of lithium-ion systems. Next slide. So what is 9540a? That's a question we get a lot of, and I'm looking through the list of participants here, and it seems like I'm sure a lot of you have a really great idea already. But for those that are just looking to dip your toes in or get acquainted, 9540a is a test method for evaluating thermal runaway propagation in battery energy storage systems. It looks at the properties of a battery undergoing thermal runaway and captures key information on the gas composition, the heat release rates, and various other temperature measurements from which fire protection engineers can then use to determine proper safety measures for installations and for protection requirements. One of the big misconceptions is that it's a pass-fail certification, but it's not a certification. Simply a data collection method. We've seen battery manufacturers come into the city saying, our battery doesn't catch fire, it's inherently safe, but all they're doing is holding a lighter under it and calling that testing. We need a more standardized method, and that is 9540a. So you can kind of see some of the work that we'll be going over here. You can go to the next slide, though. So during our conversations and even previously when we were working through the New York City Outdoor Lithium-Ion Permitting Guide, which Daniela mentioned earlier, we, along with the agencies, identified 4 main topic areas that we'd be looking into more closely, and that's thermal runaway, fire spread, explosion, and toxicity. And so during the course of about 3-month period of time last fall, we all got together with leading subject matter experts, the FDNY and Department of Buildings, to see how 9540a is applicable to each of these. Go to the next slide. So here's a first of the UL flowcharts, and they do a really great job breaking down the requirements. Here we see the test levels going from cell, module, and then unit level. Here, it's a little bit hard to see, but each of the diamonds has several of the respective performance requirements for each level of testing, and if these requirements aren't met, you move to the next level of testing, essentially. So, for example, all tests will begin at the cell level. Here, the battery cell will be forcing the thermal runaway. Generally, this is done by applying external heat to the battery in the form of like a film strip heater. If it can't be forced into thermal runaway, it's described by temperature increase, flaming gas venting, or internal short circuit. No deflagration hazard is demonstrated, and no further testing is required. If it does go into thermal runaway, you move on to module level testing and so on. And you kind of see a simplified diagram here on the right. You can go to the next one. Next is the fire propagation assessment flow chart for the installation level test. Hit next again. So we just simplified this again. Note in the bottom right-hand corner of the diagram, there's some issues to consider. And these really serve as a guide for what the HJs and fire protection engineers should be looking at. Go to the next slide. Lastly, the deflagration protection assessment chart. And I'm gonna leave it to Victoria to do all the heavy lifting from here on out. So Victoria is one of our great consultants. She's done a lot of great work with us over the past few years. So take it away, Victoria.
As Mike noted, there are these 3 sort of central flowcharts that are included in the appendix of UL9540a. And UL9540a goes through a lot of detailed steps for a lot of different types of technologies, different types of installations. And the goal of these flowcharts was to, in a single sort of format, or actually in this case in 3 different flowcharts, to identify the process, overarchingly, how a system would move through the UL9540a testing procedures, and also what analysis could be done in order to make that data, not just data, but useful to AHJs and to system designers, developers, and installers. So what you'll see throughout the next several slides, or rather the rest of the presentation, is essentially how does New York City want to see that data utilized? So the UL9540a flowcharts give a very useful baseline, and there are still local decisions that need to be made by the authorities, FDNY and Department of Building. So as we go through this, what we've done is through a call-out system, as was shown in sort of the 3-pager that's available on the Smart DG Hub website, is that we've annotated these flowcharts to expand them and make them relevant directly to New York City policy and requirements. So all of the things that you're going to be seeing over the next couple of slides are the best available thinking on what do New York City AHJs need to see when you're submitting an application. This available thinking, as Mike noted, was through coordination with the New York City AHJs and the subject matter experts But as with everything, and especially with a technology that's maturing rapidly and an industry that's maturing rapidly, things are, of course, subject to change. But these are the best available thinking at the current time. And as I've noted, these guidelines are available and published for you to review after this webinar. So if you go ahead and get started, Daniela, you can just click one more time. You'll see these pop-ups come out throughout the rest of this presentation, as I have noted, and they're going to cover three main topic areas. First will be documentation requirements, sort of data sourcing, how do you present that data, what reporting needs to look like. The second will be what are acceptable assumptions. So when you get all of this data, what are your then input assumptions that are acceptable based on currently best available thinking to the authorities that are reviewing your permitting application. And then finally, the third topic area is sort of acceptance criteria. So now that you've done your data analysis, how does that feed into your site design or system design? So starting here with the first chart, which is the fire propagation assessment flow chart, which pretty much outlines the entirety of the testing procedures from the cell to the module to the unit level. The first thing we wanted to highlight is that this testing can be done by a wide variety of laboratories. UL, of course, developed the test and they conduct it, as do other laboratories. But of course, we want to make sure that the data that's being received is produced in a consistent and replicable manner and is aligned with the practices outlined in UL9540a. To that end, while there are not a large number of accredited laboratories available to UL9540a's testing methodology itself, New York City has currently determined that it is acceptable to submit testing data from other laboratories as long as they are accredited to conduct either UL9540 or UL1973. It's recognized that these tests are not identical to UL9540a, but the understanding is that if a laboratory is accredited to one of those standards, that they will have the understanding and intelligence to determine what they need to do in order to align with the requirements in UL9540a. As such, until accredited laboratories are available, data can be accepted from those laboratories. In general, the contents of the UL9540a test report, to sort of dive into the documentation side of things, are hopefully going to be following a very similar pattern. And this is to allow authorities to quickly review these documents that are deeply technical and can have many, many reams of data. So we're looking for, in every test report, an executive summary, an indication of what laboratory conducted the test, the date of the test, the edition of the test method, which the current edition is the 4th edition, although there is some allowance for earlier editions. Well, the 4th edition is, of course, the best and the brightest, newest and greatest. So be looking, moving forward with newer installations to comply with the most recent version. The description of the energy storage equipment, so what equipment is being tested, depending on the test level. It may be the cell, module, unit, which is typically associated with a rack, or installation. Description of the layout and mitigative systems. So when we say mitigative systems throughout this, we're using it sort of as a catch-all phrase for any sort of suppression agents or fire protection agents. Description of the test setup. So making sure that you have a description of the test setup will allow for verification that the test setup aligns with UL9540a's testing methodology description. A summary of results. Again, this summary of results is understood that when you do conduct the entirety of the test, it is a multi-hour, highly monitored test. There are gigabytes and gigabytes of data that align with each of these tests. However, the summary of results should outline the high-level and most important features, such as chemical composition, off-gas temperatures, off-gas volumes, etc. And if deemed necessary by the local authorities, they may request those gigabytes and gigabytes of raw test data if they want to do a little bit of more digging. You can click one more time, Daniela. So a thing that comes up quite a bit is, does my system have to go through this? I know that Mike already described the systems that have this as a requirement. The long and short of it is that for New York City, it's applicable to all system sizes, types, installation locations, and that there will be no exceptions granted for this test. You can go to the next slide. So I want to walk through in a little bit more detail each of the test levels. So the cell test level measurements, as I've noted, you'll want to have a summary of the test results. So these are some of the critical ones that will influence the design most. Thermal runaway initiation method. By determining that, you'll know how to create thermal runaway within the module and unit level test. Cell surface temperature at gas venting and at thermal runaway, if it goes into thermal runaway. This will determine what your threshold criteria are for future tests. Gas volume released, gas composition released. This is particularly critical at the cell level because that gas composition helps you determine the following three criteria: the lower flammability limit, deflagration pressure, and burning velocity. All of these are determined through secondary tests. And in summary, we'll get into it a little bit later, but in summary, this cell level composition data will be leveraged at a larger scale when doing design for a unit or installation level design. So you can click to the next slide. For the module level measurements, you're going to be looking, you've started your thermal runaway within a single cell. You'll be looking to see all of essentially the same data that you've seen before, but in addition to that, be observing for how the system is reacting to the thermal runaway, if it's propagating, if there's flaming, where that flaming is coming from, if there's any sort of flying debris, and what the peak heat release rate is of the system in total. And these other items, as I've noted. This is helpful, again, as Mike had noted, that there are some performance criteria. If it's determined that the peak heat release is not sufficient to engage in an adjacent module, then the module level test may be the highest level test that you need to complete. You can go to the next slide. As I've noted here, and apologies, I got a little bit ahead of my boxes here, but if you need to go to the next level test, you use the module level test to determine this. So this module level data is really important because it may, if the system is designed as such that it doesn't propagate beyond the module, you may be able to stop your destructive testing at the module level. You can go ahead to the next slide. The unit level test utilizes the modules and cells that were tested in the prior iterations. You utilize the same thermal runaway methodology, and you continue to measure, again, very, very similar pieces of information. You want to see the peak heat release rate. You want to see if there's any venting or flying debris. In addition to that, you want to see if any non-active or rather integrated suppression systems act as they're supposed to and are successful in containing the hazard. When I note integral or integrated suppression systems, these are systems that are included within that unit level. It wouldn't be a container level solution or a room level solution. So integral suppression might be at a module level that then gets triggered when you get into the unit level testing. Again, if you observe, and you can click to the next one, Daniela, if you observe that there is, that the readings that you get determine that you don't need to proceed onto the next level of testing, then you can stop testing there. For the standards that need to be reviewed beyond simple testing, there is also construction review standards. New York City doesn't particularly dictate these, but anticipate that they should include at least a review of what the chemistry is, a review of the energy density of the facility or the unit, a review of what the packaging materials are, so if they're plastic, metal, et cetera, and a review of the system design and spacing. So if there's inherently protections created by having an air gap, for example. The reason that this is critical is because the testing laboratory is responsible for dictating whether or not a particular test conducted on a very particular cell model, module model, and rack model is applicable to any other system. So for New York City, it has been understood that, there's lots of very small variations that may occur between system types produced by the same manufacturer. So it's recognized that identical data may not be necessary as long as you use this quote-unquote worst-case scenario system. So when you're doing a construction review, when a lab is doing a construction review, this is critical because it helps them to determine, is this the worst-case scenario solution? So, does it have, maybe one feature is the highest energy density of a range of products. Does it have sufficiently similar architecture such that you can actually make a good apples-to-apples comparison between it and the technology that you haven't yet tested? Does it include spacing between cells that is known from other testing to provide somewhat of a barrier of thermal runaway cascade? So by completing this construction review, you then can determine which was the worst case scenario and potentially use that data in lieu of having data for the local specific site that has been selected, the local specific system that has been selected. Scaling down of those results, so say you have a module that has a very high energy density, it's the highest in its range, but you have another module that it's identical cells, identical architecture, but it just has fewer cells within the same type of module using the same type of cell. Scaling down those results are not currently acceptable. So what you may do is if you have a smaller system, you can use that worst case scenario data. You don't necessarily have to retest that identical system, but you won't have the advantage of saying you could scale that down. So whatever protections would be for the larger system size, you would have those same protections for the smaller system size. And that's simply because having that comparative model of that scaling down is not quite available yet, and it's not currently acceptable by the local authorities. You can go to the next slide. This is a critical feature that I want to make sure is highlighted. A site-specific risk analysis is necessary, and it needs to be signed and stamped by a New York State professional engineer. So there are some recommended procedures that you can use and reference materials you can use to create an acceptable risk analysis. For example, in the DOB bulletin, ISO 31010 is referenced as a methodology for conducting a risk analysis. But this is particularly critical because each site needs, especially large-scale sites, may need to be considered for what impact they can have on the surrounding area and how both facility occupants and first responders may be impacted by a failure event in an energy storage system. So this site-specific risk analysis will provide authorities with the appropriate information that they need to determine if particular site-specific changes need to be made to the protection plan because of particular hazards on that site. So this analysis includes, as you see here, identification of hazards, severity and likelihood assessment, the modes and mitigation analysis, and a gap analysis. And that gap analysis is particularly impactful to understand, okay, well, this particular site, it's located right next to a gas station. And we want to make sure that because there's something nearby that is known to be flammable, we want to make sure that we have an additional protection. Just as an example, this hasn't particularly come up, but this is the type of thing that you want to consider what's around you. And it's very helpful to the authorities as they determine their acceptance of your application. You can go on to the next slide. The toxicity analysis, however, because we're talking about outdoor systems, is not required. It is understood based on testing data that is currently available that outdoor systems will allow for sufficient diffusion of those released gases in the case there is an event. So toxicity analysis is not particularly required at this time, although indoor sites may require additional analysis and are not really being directly addressed right here within these guidelines. You can go to the next slide. So now we're moving on to the next level. So this takes us from the unit level to the installation level. And this is, again, a continuation of the fire propagation assessment flowchart. So if you're conducting a fire spread analysis, as Mike had noted, there's sort of these four critical areas that we're reviewing, and one of them is fire spread. And when you conduct a fire spread analysis, it's recognized that there may be multiple different methodologies that can be used that are all industry validated and acceptable. However, we want to make sure that they follow a similar format. So the reporting format here is outlined as including an executive summary. Again, we want to have those high-level takeaways right at the top. The methodology used. So if it was directly from UL9540a measured test results, or if there were heat transfer calculations conducted, what the data input was. So this should be from the UL9540a test data, but just understanding exactly what was taken, if there were any assumptions made or averages taken, the resultant output, and all calculations and assumptions, as well as validation documentation if it was plugged into some sort of model. Finally, any reporting that's submitted for review and approval of the local authorities does need to be signed off by a New York State PE within the final design. You can go to the next slide. It's recognized, one of the things that comes up in UL9540a and that we've heard feedback from industry on is that, it's quite conservative, the criteria that are being selected. This is understood. We recognize that the cell vent temperature, which is used as a pass-fail criteria, is not the same as the thermal runaway temperature, but the concern is that there is thermal runaway potential. And so in all cases, conservative criteria are assessed. And I would recommend, as you look at these different methodologies for conducting an assessment, that you always take the most conservative approach, because that is recognized as being the largest reduction of risk for people, first responders, and facilities. You can go to the next slide. As previously noted, we're looking at quote-unquote worst-case scenarios in some circumstances. It's recognized that a test setup is not going to look identical to a real-world installation. One of the ones that comes very quickly to mind is the fact that for the test setup, you want to have the walls be painted black. This is done for a number of reasons to make sure that the testing is consistent across the board, but that's not necessarily going to be the real-world scenario when you install it. So it's recognized that the testing scenario is not going to identically match the installation scenario, and for any differences between the testing setup and the final installation setup, there would be a requirement for a New York State PE to sign off on the differences and make sure that the test is applicable. You can go to the next slide. As is noted through a number of callouts here, if you are using fire-rated materials on, say, a structure, I know that one that comes up quite a bit is on residential installations. That material is not necessarily directly tested through UL9540a. There's a note that the max temperature, wall temperature criteria applies only for combustible wall construction. So it doesn't directly address any fire-rated walls or non-flammable walls, non-combustible walls. So again, as with many of these other determinations, if a New York State PE reviews the test data and recognizing that there may be an additional fire protection barrier in there, signs off on the design, this is acceptable to the authorities. One note here is that any sort of temperature pass-through in a wall should be taken into consideration, especially in the case that a container or an energy storage device is on the outside of a building that has materials on the inside. For example, a detached garage that may have paint or other supplies inside that garage, that it's not an empty space. So it's recommended that those temperatures are taken into account by the New York State PE. You can go to the next slide. One of the notes here within the UL9540a typical chart is this box that says issues to consider. And one of them is on the active fire mitigation methods. There's lots of methodologies for suppressing fires that are outlined in NFPA through a variety of different standards. NFPA 15 is specifically referenced by New York City authorities for quote-unquote dry pipe water-based suppression systems. This prescriptive measure is intended to allow for the inclusion of dry pipe in outdoor energy storage installations where suppression may not be mandatory based on certain determinations from the test, but where that dry pipe is desired as a methodology by which the authorities or the first responders can get water directly into the container in order to suppress any event that may occur. So you can see here outlined which ones that this requires. Small systems have no NFPA 15 requirement. Medium systems may have an NFPA 15 requirement if it's demonstrated as necessary by UL9540a. And large systems are required to have this dry pipe requirement unless it's demonstrated as not necessary, which would be a separate variance process to apply for. You can go along to the next slide, Danielle. So this is sort of the acceptance criteria or sort of acceptable final design criteria that we were talking about earlier, one of the three topics, documentation, acceptable assumptions and methodologies, and acceptance criteria. So this is currently in process, but it's necessary to determine what the fire threat may be to bystanders, facilities, and first responders. So in the next few slides, you'll see that us walk through those different hazards and acceptableness of different hazards. So what you can see here is sort of an initial design on the fire threat to building and the related sort of minimum expectations around what threat is allowable. So the temperature at which the building will be affected beyond that deemed acceptable for the performance group, as you can see in this diagram below, must consider the materials of the building and what's in the building. And so essentially, if we look at this chart, we say magnitude of event. So potential for small but infrequent events, ranging up to very large but intense events, and the impact that it can have on the facility. So saying a small event, let's say a window gets broken, being a small facility event, whereas a very large event would be considered, the building collapsing. When you see increasing levels of performance, these performance are determined to be what is the not importance is not quite the right word, but what is the requirement for this particular structure? Say the structure is, a high school that's pretty constantly occupied. The performance criteria for that would be much, much higher. So, maybe a window breaking is okay, maybe, but a building collapse would be completely unacceptable. Whereas a performance group where the facility has less of an impact, an empty scaffolding structure, if it collapsed, it would have less of an overall impact on human health as well as the area. So that's the way that this is framed, is understanding the risk associated with the size of an event and understanding the impact, what the impact means for the particular structure. So when you're looking at the hazard of a fire to a building, that's sort of the frame that is being considered for your design. You can go to the next slide. The fire threat to first responders, what we've utilized here is the Fire Protection Handbook. There's a particular heat flux at which the human body is impacted. So the determination is that at the place where the first responders need to be in order to appropriately address a hazardous event, a fire of some sort, should be less than 2.5 kW per meter squared based on the proposed siting. So the baseline is that you cannot have this fire department connection, and this connection includes any sort of piping, the dry piping that was mentioned earlier, emergency stops, monitoring equipment, et cetera. That point should not allow the first responder to feel anything more than 2.5 kW per meter squared, and in no case would be less than 10 feet away from the container. So this can be done, again, as mentioned earlier, through modeling and calculation or through direct measurement from the UL9540a testing. You can go to the next slide. For the fire threat to bystanders, it is understood that prescriptively, egress pathways will be no less than 10 feet between the system and that egress pathway. And so that threat is determined prescriptively such that the bystander is expected to be exiting the area and will have limited exposure to any sort of fire event. And so that prescriptive requirement is non-negotiable. You can go to the next slide. So the final portion of this presentation is around the deflagration analysis. So this is related to any sort of explosion that may occur because of the gases that are released under thermal runaway conditions and potentially cascading and producing large amounts of flammable or explosive gases, explosive being if they are not triggered through an ongoing fire. So the reporting requirements in here are similar to the others, which is one, that you need to have an executive summary. You need to give your data input and output. You need to give all of your calculations and assumptions and validation documentation if you use a model. And the final design of the deflagration panels or exhaust system does need to be signed off by New York State PE. One thing I want to highlight here is that NFPA 68, which is related to deflagration panels and explosion release methodologies, and NFPA 69, which is related to explosion prevention, so typically exhaust methodologies, are both acceptable. There is also some consideration for equivalent methodologies, recognizing that NFPA 68 and 69 do not directly reference battery energy storage systems. And again, this analysis would need to be signed off by New York State PE in the case that it is divergent from sort of the specified norm. You can go to the next slide. The input data for the analysis, as I sort of hinted to at the beginning of this session, is based on the cell level data. So you will have done throughout the UL9540a testing these sub-tests to determine the maximum pressure, the LFL, lower flammability limit of gas, and the burning velocity of the gas. These three inputs can be put into the models or calculations that are defined in NFPA 68 and NFPA 69 to help you to determine what the effectiveness or impact of an explosion could be within the container, and if the designed container is sufficient to contain that explosion effect, requires some sort of mitigation, such as a deflagration panel, and if it's finally, if it's appropriately sized and effective. In addition to the cell level composition data, in order to do that analysis, you need to know what the total volume is. You would utilize the unit level volume of released gases and overlay the composition found in the cell level data. So essentially, you're taking the worst case scenario composition and characteristics of the cell, and you're laying them over the total released gases pre-flaming in the unit level test. The reason that you're using the pre-flaming gas is that it's recognized that if the gas is on fire, it will not be collecting and therefore would not be an explosive hazard. So you can go to the next slide. It is recognize that there's a lot of different ways that these tests can go. You're setting on fire a large device, and it can propagate in a number of different ways. So as such, if the test was terminated for any reason, that test termination does not invalidate results. Rather, the results are still acceptable up to the termination of the test, recognizing that they may not be the same as a test that has continued onward, but also recognizing the data collected is still valid and useful. First responder impact may not be considered to impact analysis. We've noted here either positively or negatively. For example, in your analysis of the explosion hazard, if you were to claim that, well, the first, FDNY, they always respond very rapidly, I will cut off my analysis at 10 minutes because I know that they'll be there on site to take care of it. That cannot be included in the analysis, nor can a negative impact be included in the analysis. For example, saying that somebody came on site and turned on the exhaust, and by turning on that exhaust, drew in air that had sufficient oxygen to precipitate an explosion. So neither of those analyses are necessary or allowed to be submitted. You can go on to the next. For the ventilation rate, just based on the way that UL9540a is designed, there is by necessity a large ventilation rate within your container. It is recognized, or your facility, it is recognized that the energy storage system may have a different flow rate for air. You would be able to calculate that through a mass flow rate. There is an allowance for doing a model basis, but it's not necessary. You can go to the next. Just for clarity, excuse me, the volume of the enclosure is defined as the full volume of the space minus obstructions. There does not need to be the level of detail of if there's gaps between cells. You can just view a module as a solid block. You can go on to the next. I know that we've already noted that NFPA 6869 or an alternative are acceptable. Both of them are accepted for explosion analysis, but currently, based on the code that is and rules that are published in New York City, NFPA 68 is required by code, but NFPA 69, if you want to do it in addition, is optional. If there was a desire to pursue NFPA 69 instead, this would have to be pursued through a variance and would undergo a longer process to determine if it's still acceptable. In all cases, NFPA 68 is both recommended and required. We'll continue to the next. For energy storage systems, and this goes back to the NFPA 69 conversation again, if you look in different codes, this 25% LFL is referenced a number of times. This is not necessary to validate if you're not pursuing NFPA 69 as your explosion mitigation measure. However, it's recognized that if you're utilizing this to minimize any events, that 25% LFL is sort of the industry standard design. And I know, the focus of today has been on lithium ion, but it goes without saying that if gases are generated under normal conditions as defined by code, lead acid is a good example, they do have to comply with the 25% LFL requirement for normal ventilation. You can go on. It is recognized that gas detection equipment is not fully standardized at this time, so there's not a requirement to include it within the system. You can go on. This is going to get into a little bit of the nitty-gritty of the process, but one, deformation of containers is permissible. NFPA 68 has different design criteria, whether deformation is or is not permissible, if rupture is not permissible. Rupture is not permissible, deformation of container is. So it can bend, but it cannot break. The deflagration vents in all cases need to be designed with upward pressure relief, so the panels should be on the roof of the container. And this is to keep the hazard away from first responders. If you go to the next one, I apologize, click right ahead. And then click one more time, and you'll see that model-based design is permissible, but there has to be a sign-off demonstrating that by a New York State PE that it is acceptable for the design. So if you utilize a model, there needs to be validation, as previously mentioned. And if you go ahead, Daniela, next slide. Just as with the fire modeling, you have the same sort of criteria here for explosion modeling. The threat to facilities need to be considered in the same manner as was previously defined. So I won't go over that again, and I know that we're coming to the end of time. I want to save some time for questions. If we go to the next slide. Again, for pressure waves from an explosion, there is a reference here. So the threat to first responders must be less than 1 psig of overpressure at the fire department connection based on the proposed siting. Again, to reiterate, this will be no less than 10 feet from the container, but that distance may change upward if the threat at 10 feet is determined to be over 1 psig overpressure. Go ahead to the next slide. I believe the last slide here. Finally, beyond pressure, there is from an explosion a potential of a fireball. That fireball should be the sort of the hazard zone, or from that fireball would be determined based on the NFPA 68 method, which we've got a little screenshot on here. And the FTC and building should be beyond that hazard zone. And I think there's just one more note here. So, and then finally, in any explosion, there's a threat of projectiles. Again, this should be done in compliance with NFPA 68, with UL9540a demonstrating no projectiles in its tests, with additional requirements that only securely mounted equipment is permitted in the energy storage space. And finally, verifying that the system has been designed aligned with best practices, and the deflagration equipment is hinged or connected to the container. So with that, I'll hand it back over to Daniela.
Okay, thank you so much, Victoria. We just have a few minutes left, so I'll wrap up here quickly. Next steps relating to this sort of larger 9540a questions and needs for clarification. We are hoping to get at some point done later this year. We're hoping to establish some engagements with the fire protection engineer community in the area. This is the key stakeholder group that will be very involved in the, conducting the analytics around, around this testing. Another area of work that we will be pursuing again over the coming months is to conduct education and outreach to the larger industry community, especially manufacturers, around a new FDNY requirement as established in the rule published in October, that battery equipment will need to receive a certificate of approval by the FDNY. This essentially establishes, each particular battery equipment type as okay for installation in the New York City market. So keep an eye out for announcements around that. And then finally, of course, we aim to turn our attention to similar efforts around identifying best practices and guidance for installation of indoor battery systems. We have a couple of questions which I think will be useful for the entire audience to hear, so we can go through those, I think, just very briefly. First of all, before getting to the technical questions, we've recorded this webinar. We will post the recording, and we will also make the slides available. Those will both be on our website. And the first question that we received was what approved testing data or reporting is acceptable for non-lithium ion batteries if UL9540a isn't available? Victoria, do you want to jump in on that one?
Sure. UL9540a is the standard that's being leveraged. I recognize that still under, that there's not every single chemistry can be called out, but that would need to be determined through sort of a conversation with the testing laboratory to determine how to test that particular device aligned with UL9540a if it's not specifically called out. So sort of as was sort of mentioned a few times, if you work with either the testing authority or with a New York State PE, the authorities are relying on the understanding of those groups to help define what would be acceptable.
The next question that we received was, does the 9540a requirement apply to all battery technologies or just lithium-based technology? I actually sent a message to the asker of the question with the best way to get more information about this is to review, if you have not already done so, the Fire Department's Rule 608.1. This outlines this rule applies to all battery technologies, not just lithium ion, and establishes when 9540a testing is required, and for smaller system types, non-lithium batteries, it is not a requirement to get 9540a testing. There is a explosion analysis requirement for large systems. So I encourage everybody to, familiarize yourself with that information that is contained in the FDNY rule. Victoria, I don't know if you might have a little additional details to add on that as well.
No, I think you covered that well.
Okay. And then the last question, which I think we're just right at the end of the time. Please confirm that any size storage battery, whether small or large, needs this testing process. And it's a similar answer that I just gave the previous question, which is that any size lithium-ion chemistry does require the testing, whereas 9540a explosion testing, fire testing is not required for non-lithium battery types until you get into the larger systems where, as I said, more information is outlined in the FDNY rule. If anybody has other questions and you'd like to submit them to us, please use the email that's on the screen, smartdghub@cuny.edu. We'll be happy to get back to your questions, provide you more information, and especially if you want to be informed on future events, webinars, trainings, et cetera, that we're offering, reach out and we will add you to our DG Hub Roundtable. It's the announcement vehicle that we use for all of our work and publications, and we hope you will join us at our future events. Thank you all.